Beneath the ground you walk on, beneath the cities you live in, beneath the oceans you sail across, there is a force so powerful, so ancient, and so relentless that it has shaped every mountain, carved every valley, and split apart entire continents over billions of years. It is a force that builds and destroys, that creates breathtaking beauty and unleashes devastating catastrophe. It does not sleep, it does not stop, it does not care about borders, politics, or human ambition. It is the movement of the Earth's tectonic plates, and it is happening right now, right beneath your feet, as you listen to these very words. Please let us know in the comments where you are watching this documentary and what time you are watching it, and be sure to subscribe to the channel for future videos. Welcome to the story of tectonic plates. This is not just a story of geology, it is the story of our planet itself. It is the story of how Earth became what it is today, and what it will become millions of years from now. Every continent, every ocean, every volcanic eruption, every earthquake, every hot spring, every towering peak of the Himalayas, every deep trench at the bottom of the Pacific, all of it traces back to the incredible, ceaseless motion of the tectonic plates. So let us begin at the very beginning with the planet itself. When Earth first formed roughly 4.5 billion years ago, it was nothing like the world we know today. It was a molten, violent sphere of rock and metal, bombarded by asteroids, comets, and debris left over from the formation of the solar system. The surface was a churning sea of magma, glowing red and orange, with no solid ground to stand on and no atmosphere that any living thing could breathe. There were no continents, no oceans, no mountains, and certainly no life. It was, by any measure, a hellscape, but over hundreds of millions of years, something extraordinary began to happen. The surface of the Earth started to cool. A thin crust of solid rock began to form on top of the molten interior, like a skin of ice forming on a pond in winter. This crust was fragile, constantly broken apart and reformed, but gradually it became thicker and more stable. Beneath it, however, the interior of the planet remained unimaginably hot, driven by the radioactive decay of elements deep within the core and the residual heat from the planet's formation. And it is that internal heat that would set the stage for everything that followed. You see, the Earth is not a solid ball of rock, far from it. The planet has layers, and understanding those layers is absolutely essential to understanding tectonic plates. At the very center lies the inner core, a ball of solid iron and nickel roughly 1,200 kilometers in radius, compressed to a solid state despite temperatures that exceed 5,000 degrees Celsius, temperatures comparable to the surface of the sun. Surrounding the inner core is the outer core, a layer of liquid iron and nickel roughly 2,200 kilometers thick. It is the movement of this liquid metal that generates the Earth's magnetic field, the invisible shield that protects life on the surface from the deadly radiation of space. Above the outer core lies the mantle, an enormous layer of semi-solid rock roughly 2,900 kilometers thick. The mantle makes up about 84% of the Earth's total volume. It is not liquid, but it is not entirely solid either. Under the immense pressures and temperatures found at these depths, the rock of the mantle behaves somewhat like a very thick, very slow-moving fluid. It flows, but it flows on timescales that are almost incomprehensible to the human mind. A parcel of rock in the mantle might move only a few centimeters per year, yet over millions and billions of years, that slow movement has reshaped the entire surface of the planet again and again. And finally, sitting on top of the mantle like pieces of a cracked eggshell is the crust, the thin, rigid outer layer of the Earth. The crust is by far the thinnest layer of the planet. Under the oceans, the crust is typically only about 5 to 10 kilometers thick. Under the continents, it is thicker, ranging from about 30 to 70 kilometers. Compared to the nearly 6,400-kilometer radius of the entire Earth, the crust is remarkably thin, almost negligibly so. If the Earth were the size of an apple, the crust would be thinner than the apple's skin. Now here is where things get truly interesting. The crust and the uppermost part of the mantle together form a rigid layer known as the lithosphere. The lithosphere is broken into large pieces, and those pieces are what we call tectonic plates. They are not fixed in place. They move, they shift, They grind against each other, pull apart from each other, and slam into each other with forces that are almost beyond comprehension. And it is this movement that drives nearly all of the major geological processes on the planet. There are currently recognized to be about 15 major tectonic plates and several dozen smaller ones, sometimes called microplates. The largest of all is the Pacific Plate, which underlies most of the Pacific Ocean and covers an area of roughly 103 million square kilometers. It is an oceanic plate, meaning that it is composed primarily of dense basaltic rock. Other major plates include the North and South plates of the Western Hemisphere, the Eurasian Plate, the African Plate, the Antarctic Plate, the Indo-Australian Plate, and the Nazca Plate, among others. Each of these plates is in constant motion, driven by forces deep within the Earth. But what actually makes these enormous slabs of rock move? This was one of the great mysteries of geology for centuries, and the answer lies in the behavior of the mantle beneath the lithosphere. Deep within the mantle, heat from the core causes rock to become slightly less dense, causing it to rise slowly toward the surface. As it rises and moves away from the heat source, it cools, becomes denser, and begins to sink back down. This creates a circulation pattern known as a convection current. You can see this same principle at work in a pot of water heating on a stove. The water at the bottom, nearest the heat, rises to the surface, while the cooler water at the surface sinks back down. In the mantle, this process happens on a vastly larger scale and at an almost unimaginably slow pace, but over millions of years, these convection currents exert tremendous forces on the tectonic plates above. There is also another force at work called slab pull. When an oceanic plate collides with a continental plate, the denser oceanic plate is forced beneath the lighter continental plate in a process known as subduction. As the edge of the oceanic plate sinks into the mantle, it pulls the rest of the plate along with it, much like a heavy blanket sliding off the edge of a bed under its own weight. Many geologists believe that slab pull is actually the single most important force driving plate movement. A third force, known as ridge push, also contributes. At mid-ocean ridges, where new oceanic crust is being formed, the newly created rock is hot and elevated. As it cools and moves away from the ridge, it slides downhill under the force of gravity, pushing the plate along. Together, these forces, convection currents, slab pull, and ridge push, keep the tectonic plates in constant motion, reshaping the surface of the Earth in an endless cycle of creation and destruction. The idea that the continents move is not a new one. As far back as the late 16th century, mapmakers noticed something remarkable. The coastlines of Western Africa and Eastern South and Central regions of the Western Hemisphere seem to fit together like pieces of a jigsaw puzzle. It was an observation that was hard to ignore, and over the centuries, a number of thinkers proposed that these landmasses might once have been connected. But the first person to develop a comprehensive scientific hypothesis about continental movement was the German meteorologist and geophysicist Alfred Wegener. In 1912, Wegener proposed what he called continental drift, the idea that all of the continents had once been joined together in a single supercontinent, which he named Pangaea, a word derived from the Greek for all Earth. Wegener argued that Pangaea had begun to break apart roughly 200 million years ago, and that the continents had slowly drifted to their current positions over the intervening time. Wegener marshaled an impressive array of evidence to support his hypothesis. He pointed to the matching coastlines of Africa and the landmass across the Atlantic. He noted that identical fossils of ancient plants and animals had been found on continents that are now separated by vast oceans, fossils of the reptile Mesosaurus, for example, which have been found in both southern Africa and the eastern coast of the southern continent across the Atlantic. He highlighted similarities in rock formations and geological structures on different continents. He even pointed to evidence from ancient climates, noting that glacial deposits had been found in tropical regions, suggesting that those regions had once been located near the poles. Despite the strength of his evidence, Wegener's hypothesis was met with fierce resistance from the scientific establishment. The main objection was simple but devastating. Wegener could not explain the mechanism by which continents moved. He suggested that the continents plowed through the oceanic crust like ships through water, but physicists quickly showed that this was physically impossible. The forces required would be so enormous that the continents would shatter long before they could move. Without a convincing mechanism, Wegener's idea was dismissed by most geologists as speculation. Wegener died in 1930 during an expedition to Greenland, never knowing that he would eventually be vindicated. It would take another 3 decades and a revolution in geological thinking before his fundamental insight that the continents move would be accepted as scientific fact. The key breakthrough came from an unexpected place, the bottom of the ocean. In the 1950s and 1960s, new technologies allowed scientists to map the ocean floor in unprecedented detail for the first time. What they found was astonishing. Running through the middle of the Atlantic Ocean, like a seam on a baseball, was an enormous underwater mountain range, the Mid-Atlantic Ridge. This ridge stretched for thousands of kilometers, from the Arctic in the north to the Antarctic in the south, and rose thousands of meters above the surrounding ocean floor. Even more remarkable was what scientists found at the crest of the ridge. There was a deep rift valley, a gap in the rock from which molten material was welling up from the mantle below. As this molten rock or magma reached the surface, it cooled and solidified, forming new oceanic crust. The new crust then moved slowly away from the ridge on either side, like a conveyor belt, making room for yet more new crust to form behind it. This process was called seafloor spreading, and it was first proposed by the geologist Harry Hess in 1962. Seafloor spreading provided the mechanism that Wegener had been unable to identify. The continents were not plowing through the ocean floor. Instead, both the continents and the ocean floor were riding on top of the moving tectonic plates, carried along by the forces generated in the mantle below. The continents were passengers, not drivers. Further confirmation came from studies of the magnetic properties of the ocean floor. As magma cools and solidifies at a mid-ocean ridge, iron-bearing minerals within the rock align themselves with the Earth's magnetic field, essentially recording the direction and polarity of the field at the time the rock formed. Scientists discovered that the Earth's magnetic field reverses its polarity at irregular intervals, with the north and south magnetic poles switching places. These reversals are recorded in the rocks of the ocean floor as alternating stripes of normal and reversed magnetic polarity running parallel to the mid-ocean ridges. The pattern of these magnetic stripes is symmetrical on either side of the ridge, confirming that new crust is indeed being created at the ridge and moving outward in both directions. This was the final piece of the puzzle. By the late 1960s, the theory of plate tectonics had been firmly established, and it quickly became the unifying framework for understanding virtually all geological phenomena. It was, without exaggeration, one of the greatest scientific revolutions of the 20th century, comparable in its impact to Darwin's theory of evolution or Einstein's theory of relativity. Let us now turn to the different types of plate boundaries, the zones where tectonic plates interact with each other, because it is at these boundaries that the most dramatic and consequential geological events occur. There are 3 main types of plate boundaries. The first is a divergent boundary where 2 plates move apart from each other. The second is a convergent boundary where 2 plates move toward each other. And the third is a transform boundary where 2 plates slide past each other horizontally. Divergent boundaries are places of creation. As 2 plates pull apart, magma from the mantle rises to fill the gap, creating new crust. The most extensive divergent boundaries on Earth are found along the mid-ocean ridges, such as the Mid-Atlantic Ridge. These underwater mountain ranges are the longest mountain chains on the planet, stretching for a combined length of roughly 65,000 kilometers, a distance greater than the circumference of the Earth itself. At these ridges, new oceanic crust is being created at a rate of roughly 2 to 10 centimeters per year. But divergent boundaries do not occur only beneath the oceans. They can also form on land, and one of the most spectacular examples is the East African Rift System. This enormous geological feature stretches for roughly 3,000 kilometers, from the Afar Triangle in Ethiopia in the north to Mozambique in the south. Along this rift, the African plate is literally tearing itself apart. The eastern portion of the continent, sometimes called the Somali Plate, is slowly separating from the rest of Africa, and if this process continues, which it will, in tens of millions of years, a new ocean will form where the Rift Valley now stands. Eastern Africa will become a separate island continent, much like Madagascar split away from the African mainland roughly 88 million years ago. The East African Rift is a living laboratory for studying how continents break apart. The Rift Valley is dotted with volcanoes, hot springs, and lakes, many of which are remarkably deep. Lake Tanganyika, for example, is the second deepest lake in the world, with a maximum depth of roughly 1,470 meters. It fills a depression created by the rifting process and gives us a glimpse of what the early stages of ocean formation look like. Convergent boundaries, on the other hand, are places of destruction and collision, and they produce some of the most dramatic landscapes and violent geological events on Earth. What happens at a convergent boundary depends on the types of plates involved. When an oceanic plate converges with a continental plate, the denser oceanic plate is forced beneath the lighter continental plate in the process known as subduction. As the oceanic plate descends into the mantle, it encounters increasing temperatures and pressures. Water trapped in the rock is released, lowering the melting point of the mantle rock above, which causes it to melt and rise as magma. This magma can reach the surface and erupt, creating a chain of volcanoes parallel to the subduction zone. The Andes Mountains along the western edge of the South Continent across the Pacific are a classic example of this process, a towering mountain range studded with active volcanoes built by the subduction of the Nazca Plate beneath the continental plate to its east. Subduction zones are also responsible for creating the deepest features on the planet's surface. The Mariana Trench in the western Pacific, where the Pacific Plate is being subducted beneath the Philippine Sea Plate, reaches a maximum depth of roughly 11,000 meters below sea level, a depth so extreme that if Mount Everest were placed at the bottom of the trench, its summit would still be more than 2,000 meters beneath the surface of the ocean. When two oceanic plates converge, one is subducted beneath the other, and a similar chain of volcanoes is created, but this time on the ocean floor. As the volcanoes grow, they can eventually rise above the surface of the ocean, forming what is known as an island arc. The islands of Japan, the Philippines, and Indonesia are all examples of island arcs created by the subduction of one oceanic plate beneath another. The most spectacular type of convergent boundary, however, occurs when two continental plates collide. Because continental crust is relatively buoyant, neither plate can be easily subducted beneath the other. Instead, the two plates crumple and fold, pushing massive amounts of rock upward to create towering mountain ranges. The most famous example is the Himalayas, the highest mountain range on Earth, which was created by the collision of the Indian Plate and the Eurasian Plate. This collision began roughly 50 million years ago and continues today. The Indian Plate is still moving northward at a rate of roughly 5 centimeters per year, and the Himalayas continue to grow as a result. Mount Everest, the tallest mountain on Earth at roughly 8,849 meters above sea level, is getting measurably taller every year. The collision that created the Himalayas is so powerful that its effects extend far beyond the mountain range itself. The force of the collision has crumpled and deformed the crust over a vast area, creating the Tibetan Plateau, the largest and highest plateau on Earth, with an average elevation of roughly 4,500 meters above sea level. The plateau is so massive that it actually affects global weather patterns, influencing the monsoon systems that bring life-giving rains to billions of people across South and East Asia. Transform boundaries are the third type of plate boundary, and they occur where two plates slide horizontally past each other. Unlike divergent and convergent boundaries, transform boundaries neither create nor destroy crust. Instead, they accommodate the horizontal movement of plates as they shift and adjust relative to each other. The movement along transform boundaries is rarely smooth. The plates tend to lock together due to friction, and stress builds up over time until it is suddenly released in the form of an earthquake. Transform boundaries are therefore sites of frequent and sometimes devastating seismic activity. The most famous transform boundary on land runs through a portion of the western coast of the large landmass bordering the Pacific. The plates on either side of this fault are moving past each other at a rate of roughly 3 to 5 centimeters per year. Over millions of years, this movement will dramatically reshape the geography of the region. In roughly 15 million years, the land on the western side of the fault will have moved so far north that it will be adjacent to regions that are currently hundreds of kilometers away. Now, let us talk about earthquakes, because they are one of the most direct and terrifying consequences of tectonic plate movement. An earthquake occurs when stress that has built up along a fault, a fracture in the Earth's crust where movement occurs, is suddenly released. The energy radiates outward from the point of rupture in the form of seismic waves, shaking the ground and everything on it. The point within the Earth where the rupture begins is called the focus or hypocenter, and the point on the surface directly above it is called the epicenter. Earthquakes vary enormously in magnitude, from tiny tremors that can only be detected by sensitive instruments to catastrophic events that can level entire cities and kill hundreds of thousands of people. The magnitude of an earthquake is measured using the moment magnitude scale, which replaced the older Richter scale and provides a more accurate measure of the total energy released. The scale is logarithmic, meaning that each whole number increase represents roughly 32 times more energy released. A magnitude 7 earthquake releases about 32 times more energy than a magnitude 6, and about 1,000 times more energy than a magnitude 5. The vast majority of the world's earthquakes occur along plate boundaries, in zones where the interaction between plates generates the greatest stress. The single most seismically active zone on Earth is the so-called Ring of Fire, a horseshoe-shaped belt roughly 40,000 kilometers long that encircles the Pacific Ocean. The Ring of Fire follows the boundaries of the Pacific Plate in several smaller plates, and it is the site of roughly 90% of the world's earthquakes and about 75% of the world's active volcanoes. Some of the most devastating earthquakes in recorded history have occurred along the Ring of Fire. The Great Chilean Earthquake of 1960, the most powerful earthquake ever recorded, had a magnitude of 9.5 and generated a tsunami that crossed the entire Pacific Ocean, causing death and destruction as far away as Japan and the Philippines. The earthquake that struck offshore of Sumatra in December 2004, with a magnitude of 9.1, generated a tsunami that killed roughly 230,000 people in 14 countries around the Indian Ocean, making it one of the deadliest natural disasters in human history. But earthquakes do not only occur at plate boundaries. They can also occur within the interior of plates, far from any boundary. These intraplate earthquakes are less common but can be extremely dangerous, in part because they often occur in regions that are not well prepared for seismic activity. The New Madrid seismic zone, located in the central part of a large continent, produced a series of extraordinarily powerful earthquakes in 1811 and 1812 that were felt over an area of roughly 5 million square kilometers. The exact cause of intraplate earthquakes is still a subject of active research, but they may be related to ancient faults and zones of weakness within the plates that can be reactivated by tectonic forces transmitted from distant plate boundaries. Let us now explore volcanoes, another dramatic manifestation of tectonic activity. A volcano is an opening in the Earth's crust through which molten rock, volcanic gases, and ash can escape from the magma chamber below. Volcanoes can take many forms, from gently sloping shield volcanoes to steep, explosive stratovolcanoes, and they are found in a wide variety of geological settings, but the majority are directly related to tectonic plate activity. As we discussed earlier, subduction zones are prolific volcano factories. As an oceanic plate descends into the mantle, water released from the subducting slab lowers the melting point of the surrounding mantle rock, generating magma that rises to the surface. This process has created some of the most iconic and dangerous volcanoes on Earth, including Mount Fuji in Japan, Mount Pinatubo in the Philippines, and the volcanoes of the Indonesian archipelago. Divergent boundaries also produce volcanic activity, particularly along the mid-ocean ridges. The volcanic activity along these ridges is typically less explosive than at subduction zones because the magma that erupts is basaltic, with a lower viscosity and lower gas content. Basaltic eruptions tend to produce broad, flowing lava rather than violent explosions. Iceland is perhaps the most visible example of a mid-ocean ridge breaking the surface, an island built entirely by volcanic activity along the mid-Atlantic ridge. Iceland sits directly on top of the ridge, and it is one of the most volcanically active places on Earth, with eruptions occurring on average every 4 to 5 years. There's also a third type of volcanic activity that is not directly related to plate boundaries at all. These are the so-called hotspot volcanoes, which occur over plumes of unusually hot mantle material that rise from deep within the Earth, possibly from as deep as the boundary between the mantle and the core. As a tectonic plate moves over a stationary hotspot, the plume of hot material burns through the crust, creating a chain of volcanoes. The Hawaiian Islands are the most famous example. The Hawaiian island chain stretches for roughly 2,600 kilometers across the Pacific, and each island was formed as the Pacific plate moved over the Hawaiian hotspot. The oldest islands in the chain to the northwest are heavily eroded and in some cases have sunk below the surface of the ocean, while the youngest island, the Big Island of Hawaii, is currently located over the hotspot and is still volcanically active. In fact, a new island, currently known as Loihai Seamount, is forming on the ocean floor to the southeast of the Big Island and is expected to break the surface in roughly 10,000 to 100,000 years. The Yellowstone region in the interior of a large continent sits over another famous hotspot. This hotspot has produced some of the largest volcanic eruptions in Earth's history, including a cataclysmic eruption roughly 640,000 years ago that ejected roughly 1,000 cubic kilometers of material into the atmosphere, an eruption roughly 2,500 times larger than the 1980 eruption of Mount St. Helens. The magma chamber beneath Yellowstone remains active, fueling the region's famous geysers and hot springs, and while the probability of another supereruption in the near future is extremely low, the consequences of such an event would be devastating on a global scale. Volcanic eruptions can have profound effects on the Earth's climate. Large eruptions inject enormous quantities of sulfur dioxide and ash into the stratosphere, where they can block sunlight and lower global temperatures for months or even years. The eruption of Mount Tambora in Indonesia in 1815 was one of the most powerful eruptions in recorded history, and it injected so much material into the atmosphere that 1816 became known as the year without a summer. Temperatures dropped dramatically across the northern hemisphere, causing widespread crop failures, food shortages, and famine. Frost and snow were reported in June and July in regions that normally enjoyed warm summers, and the social and economic consequences were severe. Now let us delve deeper into the concept of subduction, because it is one of the most important processes in all of plate tectonics, and it has consequences that extend far beyond the creation of volcanoes and trenches. When an oceanic plate is subducted beneath another plate, it does not simply disappear. It descends into the mantle at an angle, forming what is known as a subduction slab. As the slab sinks deeper, it is gradually heated and compressed. The minerals in the rock undergo a series of transformations, releasing water and other volatile substances that have been trapped within the oceanic crust and the sediments that cover it. This process, known as dehydration, is critically important because the released water lowers the melting point of the surrounding mantle rock, triggering the melting that produces volcanic magma. Some subducting slabs have been traced by seismic imaging all the way down to the boundary between the mantle and the core, a depth of roughly 2,900 kilometers. The fate of these deeply subducted slabs is a subject of ongoing research, but it appears that they eventually assimilate into the mantle, their material recycled and eventually return to the surface through volcanic activity millions or even billions of years later. This represents a grand recycling system, one that has been operating for billions of years and that continuously exchanges material between the surface and the deep interior of the planet. Subduction is also responsible for the process known as accretion, in which sediments and pieces of oceanic crust are scraped off the subducting plate and plastered onto the edge of the overriding plate, forming a wedge-shaped mass of deformed rock known as an accretionary prism. Over millions of years, these accretionary prisms can grow to considerable size and can contribute to the growth of continents. In fact, much of the material that makes up the edges of many continental landmasses was originally scraped off subducting oceanic plates and added to the continent piece by piece over geological time. The subduction process is not always smooth. Sometimes, large pieces of buoyant material, such as oceanic plateaus, island arcs, or fragments of continental crust, are carried on the subducting plate and are too buoyant to be subducted. When these features reach the subduction zone, they are instead accreted onto the overriding plate, adding new material to the continent. These pieces, known as terranes, can have geological histories that are completely different from the surrounding continental rock. Many continents are in fact mosaics of terranes that were assembled over hundreds of millions of years by the subduction process. This is one of the ways in which continents grow over geological time. Now let us consider the relationship between tectonic plates and the oceans. The oceans, as we know them, are products of plate tectonics. Every major ocean basin on Earth was created by the process of seafloor spreading at divergent plate boundaries. The Atlantic Ocean, for example, began to form roughly 180 million years ago when Pangaea began to break apart. A rift formed between what would become Africa and the landmass to its west, and as the two pieces of Pangaea moved apart, new oceanic crust was created along the mid-Atlantic ridge, gradually widening the ocean. The Atlantic is still growing today at a rate of roughly 2.5 centimeters per year. In contrast, the Pacific Ocean is shrinking because the oceanic crust around its edges is being subducted beneath the surrounding plates faster than new crust is being created at the East Pacific Rise. This means that the geography of the Earth is constantly changing. The oceans open and close. The continents join together and split apart. And this cycle, sometimes called the Wilson cycle after the Canadian geologist John Tuzo Wilson, repeats itself over and over again on a timescale of roughly 300 to 500 million years. We are currently in the middle of a cycle. The Atlantic is opening, the Pacific is closing, and hundreds of millions of years from now, the continents will once again converge to form a new supercontinent. Pangaea was not the first supercontinent, and it will not be the last. Before Pangaea, there was Rodinia, which existed roughly 1 billion to 750 million years ago. Before Rodinia, there may have been others, including one called Columbia or Nuna, which may have existed roughly 1.8 billion years ago. And looking forward, geologists have proposed several possible configurations for the next supercontinent, which has been given names such as Pangaea Ultima, Amasia, and Navapangaea, depending on the model. Regardless of which model proves correct, the formation of the next supercontinent is expected to occur roughly 200 to 300 million years from now. The cycle of supercontinent assembly and breakup has had profound effects on the Earth's climate, ocean circulation, and the evolution of life. When the continents are assembled into a single landmass, the climate tends to become more extreme, with large interior regions experiencing very hot summers and very cold winters, far from the moderating influence of the oceans. Ocean circulation patterns are also dramatically altered, affecting the distribution of heat around the planet. And the breakup of a supercontinent creates new ocean basins, new coastlines, and new shallow seas, which can provide new habitats and drive the diversification of life. One of the most dramatic examples of how tectonic plate movement has affected life on Earth is the story of the Isthmus of Panama. Roughly 3 million years ago, tectonic activity raised a narrow bridge of land between the two large continental masses of the Western Hemisphere, closing the gap that had previously connected the Atlantic and Pacific Oceans. This seemingly small geological event had enormous consequences. It altered ocean circulation patterns throughout the Atlantic, contributing to the formation of the Gulf Stream and the thermohaline circulation that drives global climate patterns. It also allowed the migration of land animals between the previously isolated continents, an event known as the Great Interchange, which dramatically reshaped the ecosystems of both landmasses. And some scientists have suggested that the changes in ocean circulation caused by the closure of the isthmus may have contributed to the onset of the ice ages that have characterized the last few million years of Earth history. Let us now turn to the relationship between tectonic plates and mountain building, a process known as orogenesis. Mountains are among the most awe-inspiring features of the Earth's surface, and virtually all of the world's major mountain ranges are the direct result of tectonic plate interactions. We have already discussed the Himalayas, formed by the collision of two continental plates, but there are many other examples that illustrate the incredible power of plate tectonics to shape the landscape. The Alps, for instance, were formed by the collision of the African plate and the Eurasian plate, a process that began roughly 65 million years ago and continues today. The rocks of the Alps have been folded, faulted, and thrust over each other in complex patterns that geologists have spent centuries unraveling. Some of the rocks found at the summits of alpine peaks originated as sediments on the floor of an ancient ocean, the Tethys Sea, which once separated Africa from Eurasia. The closure of the Tethys Sea and the subsequent collision of the two continents pushed those sediments thousands of meters into the air, a testament to the incredible forces involved. The Ural Mountains, which run north to south through Eurasia, are another product of plate collision, but they are much older. They were formed roughly 300 million years ago by the collision of ancient continents that would eventually become part of Pangaea. The Urals are today relatively low and worn down by hundreds of millions of years of erosion, but they still serve as a geographical boundary between Europe and Asia. Mountain building is not always the result of head-on collision between plates. In some cases, mountains are formed by the compression and folding of crust at subduction zones, or by the uplift of crust over hotspots, or by the extension and thinning of crust at rift zones. The Basin and Range province in the western part of a large continent, for example, is a region where the crust has been stretched and thinned by tectonic forces, creating a dramatic landscape of alternating mountain ranges and flat valleys. Erosion constantly works against the forces of mountain building, wearing down the peaks and carrying sediment to the lowlands and ultimately to the sea. Without the continuous action of tectonic forces, the Earth's surface would eventually be worn flat by erosion. The fact that mountains exist at all is proof that tectonic forces are constantly at work, lifting and deforming the crust faster than erosion can wear it away. On a planet without plate tectonics like Mars, the ancient mountains have been worn down to gentle hills, and the surface has become geologically static. It is plate tectonics that keeps the Earth geologically alive. This brings us to a fascinating question. Is Earth the only planet in our solar system with plate tectonics? As far as we know, the answer is yes. None of the other rocky planets, not Mercury, not Venus, not Mars, show clear evidence of active plate tectonics. Mars may have had some form of plate tectonic activity early in its history, but if so, it ceased billions of years ago. Venus has a thick, hot crust that appears to periodically resurface itself through massive volcanic events, but it does not have the system of distinct, moving plates that characterizes Earth. Why is Earth unique in this regard? Several factors may contribute. Earth's oceans may play a crucial role. Water weakens rocks and lubricates faults, making it easier for plates to move. The specific composition of Earth's mantle, the presence of liquid water at the surface, and the planet's size and internal heat all seem to be important. Some scientists have suggested that the presence of plate tectonics may be one of the factors that make Earth habitable, because the cycling of material between the surface and the interior helps to regulate the planet's climate over geological timescales. Let us explore this idea further, because the connection between plate tectonics and climate is one of the most important and fascinating aspects of the entire subject. Over geological timescales, the Earth's climate is regulated in part by the carbon cycle, the movement of carbon between the atmosphere, the oceans, the biosphere, and the rocks of the Earth's crust. Carbon dioxide is a greenhouse gas, meaning that it traps heat in the atmosphere and raises global temperatures. The amount of carbon dioxide in the atmosphere at any given time is determined by the balance between processes that add carbon dioxide to the atmosphere and processes that remove it. Volcanic eruptions driven by plate tectonics are one of the primary sources of carbon dioxide in the atmosphere. When volcanoes erupt, they release carbon dioxide that has been locked in the Earth's interior. Without volcanic activity, the carbon dioxide in the atmosphere would gradually be removed by chemical weathering of rocks, a process in which carbon dioxide reacts with minerals in the rocks to form carbonate compounds that are eventually washed into the oceans and deposited as sedimentary rocks such as limestone. This process of chemical weathering acts as a thermostat for the planet's climate. When global temperatures rise, the rate of chemical weathering increases, removing more carbon dioxide from the atmosphere and causing temperatures to fall. When temperatures fall, weathering slows, carbon dioxide from volcanic activity accumulates in the atmosphere, and temperatures rise again. This negative feedback loop, sometimes called the carbonate-silicate cycle, has helped to keep Earth's climate within a habitable range for billions of years, even as the sun has gradually become brighter over time. Without plate tectonics to drive volcanic activity and to recycle carbonate sediments back into the mantle through subduction, this thermostat would not function. Carbon would be locked away in sedimentary rocks and would never be returned to the atmosphere. Over time, the Earth's atmosphere would lose its greenhouse effect, temperatures would plummet, and the planet would freeze. In this sense, plate tectonics is not just a geological curiosity. It is essential to the habitability of the planet. The connection between plate tectonics and climate goes even further. The positions of the continents have a profound effect on ocean circulation patterns, which in turn influence the distribution of heat around the planet. When continents are positioned over the poles, they can become covered with ice sheets, which reflect sunlight back into space and cool the planet further. When the continents are clustered near the equator, leaving the poles free of land, ocean currents can circulate more freely, distributing heat more evenly and producing a warmer global climate. The current configuration of the continents, with a large landmass, Antarctica, positioned directly over the South Pole, has contributed to the cold climate of the current geological period. The Antarctic ice sheet, which contains roughly 26.5 million cubic kilometers of ice, has existed in some form for roughly 34 million years, since the opening of the Drake Passage between the southern tip of South and the Antarctic continent allowed a circumpolar ocean current to develop, isolating Antarctica from warmer waters to the north and causing it to cool dramatically. This is a perfect example of how tectonic plate movement, by slowly rearranging the continents, can trigger dramatic shifts in global climate over millions of years. The current ice age, which began roughly 2.6 million years ago, is at least partly the result of the specific arrangement of the continents and ocean basins produced by hundreds of millions of years of tectonic activity. Now let us talk about a phenomenon that is closely related to plate tectonics and that has shaped human history in ways that are often overlooked: tsunamis. A tsunami is a series of ocean waves generated by a sudden displacement of a large volume of water. While tsunamis can be caused by landslides, volcanic eruptions, or even asteroid impacts, the most common cause is an earthquake at a subduction zone. When a large earthquake occurs along a subduction zone, the sudden vertical displacement of the ocean floor can lift or lower the water column above by several meters. This displacement generates waves that radiate outward in all directions. In the open ocean, tsunami waves may be barely noticeable, with heights of only a few centimeters and wavelengths of hundreds of kilometers. But as these waves approach the shore and the water becomes shallower, they slow down and pile up, sometimes reaching heights of 10, 20, or even 30 meters or more. The 2004 Indian Ocean tsunami was generated by a massive earthquake along the subduction zone where the Indian plate is being forced beneath the Burma plate. The earthquake ruptured a segment of the plate boundary roughly 1,300 kilometers long, and the resulting tsunami struck coastlines throughout the Indian Ocean, from Indonesia to Sri Lanka to the coast of East Africa. The devastation was almost beyond comprehension. Entire communities were swept away. The waves penetrated kilometers inland in some areas, and the death toll, roughly 230,000 people, made it one of the deadliest natural disasters in recorded history. The 2011 Tohoku earthquake and tsunami in Japan was another catastrophic event driven by plate tectonics. A magnitude 9 earthquake along the subduction zone east of Japan generated tsunami waves that reached heights of roughly 40 meters in some locations. The waves overtopped seawalls, destroyed coastal towns, and triggered a meltdown at the Fukushima Daiichi nuclear power plant, creating a nuclear disaster on top of a natural one. The total death toll exceeded 18,000, and the economic damage was estimated at roughly $235 billion, making it the costliest natural disaster in history. These disasters are stark reminders that the tectonic forces shaping our planet are not abstract geological concepts. They are real, present, and potentially deadly forces that affect the lives of billions of people. Let us now examine how scientists study tectonic plates and monitor their movements. One of the most powerful tools for studying the Earth's interior and the behavior of tectonic plates is seismology, the study of seismic waves. When an earthquake occurs, it generates several types of seismic waves that travel through the Earth's interior. By analyzing the speed, direction, and behavior of these waves as they propagate through the planet, seismologists can build detailed images of the Earth's internal structure. There are two main types of seismic waves that travel through the body of the Earth. Primary waves, or P waves, are compressional waves that can travel through both solids and liquids. Secondary waves, or S waves, are shear waves that can only travel through solids. The fact that S waves cannot pass through the outer core is one of the key pieces of evidence that the outer core is liquid. By analyzing the arrival times of P waves and S waves at seismograph stations around the world, seismologists can determine the location, depth, and magnitude of an earthquake with remarkable precision. They can also use the behavior of seismic waves to create three-dimensional images of the Earth's interior, a technique known as seismic tomography. These images have revealed the structure of subducting slabs, mantle plumes, and other features deep within the Earth that would otherwise be completely invisible. Another important tool for studying plate tectonics is the Global Positioning System, commonly known as GPS. By placing GPS receivers on stable bedrock at locations around the world, scientists can measure the movement of tectonic plates with millimeter-level precision. These measurements have confirmed the rates and directions of plate movement predicted by the theory of plate tectonics and have revealed subtle details of plate deformation that were previously unknown. Satellite-based remote sensing has also revolutionized the study of plate tectonics. Satellites can measure changes in the Earth's surface with extraordinary precision, detecting the slow buildup of strain along faults, the inflation of volcanic calderas as magma accumulates beneath them, and the subtle changes in the Earth's gravity field caused by the movement of mass within the planet. One of the most exciting developments in recent years has been the growing ability to image the Earth's interior in ever greater detail. Seismic tomography has revealed that the mantle is not a uniform layer of rock but a complex, dynamic system with large-scale structures that are only now beginning to be understood. Two enormous structures, known as large low shear velocity provinces, or LLSVPs, have been identified near the base of the mantle beneath Africa and the Pacific Ocean. These structures are thousands of kilometers across and hundreds of kilometers tall, and their origin and significance are subjects of intense scientific debate. Some researchers believe they are remnants of the earliest differentiation of the Earth's interior, while others think they may be related to the accumulation of subducted material over billions of years. Whatever their origin, they appear to influence the pattern of mantle convection and may play a role in determining the locations of hotspot volcanoes and the long-term movement of tectonic plates. Let us now discuss the geological timescale and the vast spans of time over which plate tectonics operates. The geological timescale is divided into eons, eras, periods, and epochs, each defined by significant events in Earth's history. The current eon, the Phanerozoic, began roughly 541 million years ago with the Cambrian explosion, the sudden appearance of a vast diversity of complex animal life in the fossil record. Before the Phanerozoic came the Proterozoic eon, which lasted from roughly 2.5 billion to 541 million years ago, and before that the Archean eon, which lasted from roughly 4 billion to 2.5 billion years ago. The earliest eon, the Hadean, covers the period from the formation of the Earth roughly 4.5 billion years ago to about 4 billion years ago. Plate tectonics, as we know it, may not have been operating during the earliest part of Earth's history. The Hadean Earth was so hot that the crust may not have been rigid enough to form plates. Some researchers believe that plate tectonics began roughly 3 to 4 billion years ago, during the late Archean or early Proterozoic, but the exact timing is uncertain and debated. The oldest rocks on Earth, found in places like the Acasta Gneiss Complex in northern Canada and the Iswa Greenstone Belt in Greenland, are roughly 4 billion years old and show some evidence of tectonic activity, but interpreting these ancient rocks is extremely challenging. What is clear is that plate tectonics has been the dominant geological process on Earth for at least the last 3 billion years, and during that time it has continuously reshaped the surface of the planet. Continents have assembled and broken apart, oceans have opened and closed, mountain ranges have risen and been eroded to nothing, and through it all the tectonic plates have kept moving, driven by the relentless heat of the Earth's interior. It is worth pausing to appreciate the sheer scale of geological time and the patient, unceasing nature of tectonic plate movement. The plates move at rates comparable to the rate at which your fingernails grow, just a few centimeters per year. It seems impossibly slow, and yet, over millions of years, those centimeters add up. At a rate of 5 centimeters per year, a plate would travel 50 kilometers in a million years, 500 kilometers in 10 million years, and 5,000 kilometers in 100 million years. Given enough time, continents can travel from one side of the globe to the other. Consider the journey of the Indian subcontinent. Roughly 140 million years ago, India was part of the ancient supercontinent of Gondwana, located near the South Pole, close to Antarctica. When Gondwana began to break apart, India separated and began to move northward at a remarkably rapid rate, sometimes estimated at as much as 15 to 20 centimeters per year, which is extremely fast by tectonic standards. Over the course of roughly 90 million years, India traveled thousands of kilometers across the Tethys Ocean before finally colliding with the Eurasian plate roughly 50 million years ago, creating the Himalayas. This epic journey from the vicinity of the South Pole to its current position in the Northern Hemisphere is one of the most dramatic examples of continental movement in the geological record. Now let us explore some of the more unusual and less well-known aspects of plate tectonics. One of the most intriguing phenomena associated with plate tectonics is the existence of ophiolites. An ophiolite is a section of oceanic crust and upper mantle that has been uplifted and exposed on the surface of a continent. Ophiolites provide geologists with a rare opportunity to directly examine the rocks that normally lie beneath the ocean floor, thousands of meters of water. Some of the most famous ophiolites are found in Oman, Cyprus, and Newfoundland. The Samel ophiolite in Oman is one of the largest and best preserved examples in the world, and it has been studied extensively to understand the structure and composition of oceanic crust. Another fascinating aspect of plate tectonics is the phenomenon of back arc spreading. In some subduction zones, the overriding plate is stretched and thinned behind the volcanic arc, creating a back arc basin where new oceanic crust is formed. This process is similar to seafloor spreading at a mid-ocean ridge, but it occurs in a different tectonic setting. The Sea of Japan, for example, is a back arc basin that formed as a result of the subduction of the Pacific Plate beneath the Eurasian Plate. Plate tectonics also plays a role in the formation of mineral deposits and natural resources. Many of the world's most important mineral deposits are associated with plate boundaries. Hydrothermal vents at mid-ocean ridges, where hot, mineral-laden water erupts from the seafloor, deposit sulfide minerals rich in copper, zinc, gold, and other valuable metals. Subduction zones are associated with the formation of porphyry copper deposits, which are the world's largest source of copper, and the collision of tectonic plates can concentrate and transform minerals, creating deposits of gold, silver, tin, and other metals. The distribution of fossil fuels is also influenced by plate tectonics. Oil and natural gas are formed from the remains of marine organisms that were deposited in sedimentary basins, often along continental margins or in rift valleys. The specific conditions required for the formation and preservation of fossil fuels, including the right types of source rocks, reservoir rocks, and cap rocks, are often the result of specific tectonic settings and histories. The vast oil reserves of the Persian Gulf region, for example, are associated with sedimentary rocks that were deposited in a shallow sea that existed between the Arabian and Eurasian plates before their collision. Even diamonds owe their existence in part to plate tectonics. Most natural diamonds form at depths of roughly 150 to 200 kilometers below the surface, in the upper mantle, under conditions of extreme pressure and temperature. They are brought to the surface by rare and violent volcanic eruptions that create narrow, pipe-shaped structures called kimberlite pipes. The carbon from which diamonds are made may have originated at the Earth's surface, in the form of organic carbon or carbonate minerals, before being subducted deep into the mantle by tectonic plate movements. In this sense, a diamond is a piece of the Earth's surface that has been recycled through the deep mantle and returned to the surface in a new and spectacular form. Let us now discuss the connection between plate tectonics and the evolution of life, because this connection is profound and far-reaching. Plate tectonics has shaped the course of biological evolution in numerous ways. By breaking apart and reassembling continents, plate tectonics has repeatedly isolated and reunited populations of organisms, driving speciation and extinction. When a continent breaks apart, populations that were once connected are separated by growing ocean basins, and they evolve independently in isolation, often developing into entirely new species. When continents collide or are connected by land bridges, previously isolated populations come into contact, and competition between them can drive some species to extinction while others thrive. The breakup of Gondwana, for example, isolated the flora and fauna of various southern continents, leading to the independent evolution of unique ecosystems. Australia's remarkable marsupial mammals, including kangaroos, koalas, and wombats, evolved in isolation after Australia separated from Antarctica roughly 45 million years ago. The island of Madagascar, which separated from mainland Africa roughly 88 million years ago, has an extraordinary diversity of endemic species, including lemurs, which evolved in isolation for tens of millions of years. Plate tectonics has also influenced evolution through its effects on climate and ocean circulation. The opening and closing of ocean gateways, such as the Drake Passage and the Isthmus of Panama, has altered the flow of ocean currents, which in turn has affected the distribution of heat and moisture around the globe. These changes in climate have created new selective pressures on organisms, driving adaptation and evolution. Perhaps the most dramatic example of the connection between plate tectonics and life is the role of volcanic eruptions in mass extinctions. The largest mass extinction in Earth's history, the Permian-Triassic extinction event roughly 252 million years ago, which wiped out roughly 96% of all marine species and 70% of all terrestrial vertebrate species, is widely believed to have been caused, at least in part, by the eruption of the Siberian Traps, an enormous volcanic province in what is now Siberia. These eruptions released vast quantities of carbon dioxide and sulfur dioxide into the atmosphere, causing rapid global warming, ocean acidification, and anoxia, a lethal combination that devastated ecosystems worldwide. The Deccan Traps in India are another example. These massive volcanic eruptions occurred roughly 66 million years ago, around the same time as the Chicxulub asteroid impact that is widely credited with causing the extinction of the non-avian dinosaurs. The relative contributions of the Deccan eruptions and the asteroid impact to the end Cretaceous mass extinction are still debated, but there is growing evidence that the volcanic activity played a significant role, at least in stressing ecosystems before the final blow of the asteroid impact. These large igneous provinces, as they are known, are among the most catastrophic geological events in Earth's history, and they are ultimately driven by processes deep within the mantle that are related to, or at least influenced by, the broader system of plate tectonics. Let us turn now to the seafloor itself and what it can tell us about the history of plate tectonics. One of the most remarkable discoveries of 20th century geology was that the ocean floor is geologically young. The oldest oceanic crust on Earth is only about 200 million years old, found in a small region of the western Pacific and in parts of the eastern Mediterranean. This is a tiny fraction of the Earth's 4.5 billion year history. The reason is simple. Oceanic crust is constantly being created at mid-ocean ridges and destroyed at subduction zones. The average age of the ocean floor is only about 80 million years. Continental crust, by contrast, can be extremely old because it is too buoyant to be subducted. The oldest continental rocks are roughly 4 billion years old, and some mineral grains, specifically zircon crystals found in Western Australia, have been dated to roughly 4.4 billion years, almost as old as the Earth itself. These ancient zircons are among the most precious objects in all of geology, tiny time capsules that preserve information about conditions on the very early Earth. The contrast between the youth of the ocean floor and the great age of the continents is one of the most fundamental features of plate tectonics. It reflects the ongoing recycling of oceanic crust through the subduction process and the relative permanence of continental crust, which accumulates and persists at the surface over billions of years. This recycling of the ocean floor means that the geological record of the deep past is primarily preserved on the continents. To reconstruct the positions and movements of tectonic plates in the distant past, geologists rely on a variety of techniques, including paleomagnetism, the study of the magnetization of ancient rocks, which can reveal the latitude at which the rocks formed and the orientation of the magnetic field at the time. By combining paleomagnetic data with information from fossils, rock types, and geological structures, geologists can construct maps of the ancient Earth, showing how the continents were arranged at different points in the past. These paleogeographic reconstructions have revealed a rich and complex history of continental movement. We know that the continents have been in constant motion for at least 3 billion years, assembling into supercontinents and breaking apart in a grand, slow dance that continues to this day. Each cycle of supercontinent assembly and breakup takes roughly 300 to 500 million years, and each cycle leaves its mark on the geological record in the form of mountain ranges, rift valleys, volcanic deposits, and sedimentary sequences. One of the most active areas of research in plate tectonics today is the study of how the system of plates and mantle convection has changed over geological time. The early Earth was hotter than it is today because radioactive elements in the interior were more abundant and decaying more rapidly. This extra heat may have made the mantle convect more vigorously, and some researchers believe that the tectonic plates of the early Earth were smaller and moved faster than the plates of today. Others have suggested that early Earth may have had a different style of tectonics altogether, perhaps something like the stagnant lid regime seen on Venus today, in which the entire surface behaves as a single plate with no subduction and no seafloor spreading. The transition from this early style of tectonics to the modern plate tectonic system is one of the great unsolved problems in Earth science. Another important question is how long plate tectonics will continue on Earth. The driving force for plate tectonics is the internal heat of the planet, and that heat is gradually being lost. The Earth is slowly cooling as heat leaks through the surface and as the radioactive elements in the interior decay. Eventually, perhaps in 1 billion years or more, the Earth may cool to the point where the mantle can no longer convect vigorously enough to drive plate motion, and the tectonic plates will grind to a halt. When that happens, the Earth will become a geologically dead planet, like Mars, with no new mountains, no new volcanoes, no earthquakes, and a gradually eroding surface. The carbon cycle will shut down, the climate will become unregulated, and the conditions that make the planet habitable will slowly deteriorate. But that is a story for the very distant future. For now, the tectonic plates are very much alive, very much in motion, and very much shaping the world we live in. Let us talk about one more subject before we close this first part of our documentary, and that is the effect of tectonic plate movement on human civilization. From the earliest days of human history, the forces of plate tectonics have shaped where and how people live. The most fertile agricultural lands are often found in valleys and floodplains created by tectonic processes. The most strategically important mountain passes exist because plate collisions pushed up towering ranges. The hot springs and geothermal resources that humans have used for thousands of years are products of volcanic activity driven by plate movement, but tectonic forces have also brought destruction. Earthquakes have toppled cities since the dawn of civilization. The ancient city of Pompeii was buried by the eruption of Mount Vesuvius in 79 AD, a volcanic event driven by the subduction of the African plate beneath the Eurasian plate. The 1755 Lisbon earthquake, one of the deadliest in European history, was caused by tectonic activity along the boundary between the Eurasian and African plates. The 1923 Great Kanto earthquake devastated Tokyo and Yokohama, killing over 100,000 people. The 2010 Haiti earthquake, with a magnitude of 7, killed an estimated 220,000 people in one of the most densely populated and least prepared nations in the world. Throughout history, human societies have had to adapt to the reality of living on a tectonically active planet. In Japan, centuries of experience with earthquakes have led to the development of some of the most advanced earthquake-resistant building techniques in the world. In Iceland, geothermal energy harnessed from volcanic activity provides heating for roughly 90% of the country's homes and generates a significant portion of its electricity. In many volcanic regions, the rich, mineral-laden soils produced by the weathering of volcanic rocks support some of the most productive agriculture on the planet, which is why so many people continue to live in the shadow of active volcanoes despite the dangers. The study of plate tectonics has also given us the tools to better prepare for and respond to natural disasters. By understanding the locations and behaviors of plate boundaries, scientists can assess the risk of earthquakes and volcanic eruptions in specific regions. Seismic monitoring networks can detect earthquakes within seconds and issue warnings before the damaging shaking arrives. Tsunami warning systems, developed after the devastating 2004 Indian Ocean tsunami, can alert coastal populations to incoming waves, giving them precious minutes to evacuate to higher ground. But despite all our advances in understanding and technology, we remain fundamentally at the mercy of tectonic forces. We cannot stop an earthquake. We cannot prevent a volcanic eruption. We cannot halt the slow, inexorable movement of the plates. All we can do is understand these forces as best we can, prepare for their consequences, and respect the awesome power of the planet we call home. This brings us to the end of part 1 of our documentary on tectonic plates. We have covered the basic structure of the Earth, the discovery and development of plate tectonic theory, the types of plate boundaries, the forces that drive plate movement, the creation and destruction of oceanic crust, the building of mountains, the triggering of earthquakes and tsunamis, the formation of volcanoes, the connection between plate tectonics and climate, and the impact of tectonic forces on human civilization. But there is so much more to explore. In part 2, we will delve deeper into the mysteries of the deep mantle, the future of the continents, the role of plate tectonics in the origin and evolution of life, the search for plate tectonics on other planets, and the cutting-edge research that is continuing to transform our understanding of these mighty forces. We will explore the geological wonders of specific regions around the world, from the volcanic islands of the Pacific to the ancient cratons of Africa and Australia. We will meet the scientists who are pushing the boundaries of knowledge, using everything from supercomputers to deep-sea submersibles to unravel the secrets hidden beneath the surface. The story of tectonic plates is the story of the Earth itself. It is a story that began 4.5 billion years ago and that will continue for billions of years to come. It is a story of creation and destruction, of beauty and catastrophe, of forces so vast and so patient that they make the entirety of human history seem like the blink of an eye. The ground beneath your feet is moving. It has always been moving, and it will continue to move long after we are gone. The only question is whether we will take the time to understand it, to respect it, and to marvel at the extraordinary dynamic planet that is our home. Welcome back. If you have stayed with us from part 1, then you already know that the ground beneath your feet is not as solid or as permanent as it seems. You know that the Earth's surface is broken into massive slabs of rock called tectonic plates, and that these plates are in constant, slow, relentless motion, driven by forces deep within the planet's interior. You know that this motion builds mountains, opens oceans, triggers earthquakes, and fuels volcanic eruptions. You know that it has shaped the geography of the Earth, influenced the climate, and altered the course of biological evolution over billions of years. But there is so much more to this story. In this second part of our documentary, we are going to go deeper, both literally and figuratively. We are going to explore the mysteries of the deep mantle, the strange and alien landscapes of the ocean floor, the geological futures that await our planet, and the remarkable ways in which tectonic forces have sculpted specific regions of the world into the landscapes we know today. We are going to examine the cutting-edge science that is revealing new truths about the Earth's interior, and we are going to consider the tantalizing question of whether plate tectonics might exist on other worlds beyond our own. So let us begin. We ended part 1 with a discussion of how tectonic plate movement has affected human civilization, from the fertility of volcanic soils to the devastation of earthquakes and tsunamis. But there is another dimension to this relationship that deserves exploration, the way in which tectonic forces have shaped the very resources that human civilizations depend upon. Consider water. Fresh water is the most essential resource for human life, and the distribution of freshwater on the planet is profoundly influenced by tectonic activity. Mountain ranges created by plate collisions intercept moisture-laden winds, forcing air upward and causing it to cool and release its moisture as rain or snow. This orographic effect is responsible for some of the wettest regions on Earth and, conversely, for some of the driest. The Himalayas, for instance, intercept the moisture carried by the Indian Ocean monsoon, producing torrential rains on the southern slopes and creating a vast rain shadow to the north, where the Tibetan Plateau and the Gobi Desert receive very little precipitation. Without the tectonic collision that created the Himalayas, the climate of all of South and Central Asia would be fundamentally different, and the rivers that sustain billions of people, the Ganges, the Indus, the Brahmaputra, the Mekong, the Yangtze, and the Yellow River, would not exist in their current form. Groundwater, too, is influenced by tectonics. The fractures, faults, and folds created by tectonic activity can create pathways for water to flow through rock and can form underground reservoirs, known as aquifers, that store vast quantities of fresh water. Many of the world's most important aquifers are located in sedimentary basins that were created by tectonic processes, including rifting, subsidence, and the accumulation of sediment along continental margins. Now let us descend into the deep earth and explore what lies beneath the tectonic plates themselves, because some of the most exciting discoveries in modern geology are being made not at the surface, but thousands of kilometers below it. We discussed in Part 1 that the mantle is a vast layer of semi-solid rock roughly 2,900 kilometers thick, extending from the base of the crust to the top of the outer core. But the mantle is not a uniform, featureless layer. It has structure, complexity, and dynamics that scientists are only now beginning to understand. One of the most important boundaries within the mantle is the transition zone, which lies at depths of roughly 410 to 660 kilometers. At these depths, the immense pressure causes the minerals in the mantle rock to undergo a series of phase changes, transforming into denser crystal structures. These phase changes affect the way the mantle convects, and the transition zone may act as a partial barrier to the movement of material between the upper and lower mantle. For decades, geologists debated whether convection in the mantle occurs as a single, whole mantle circulation, with material flowing from the surface all the way to the core mantle boundary and back, or whether the upper and lower mantle convect separately, with the transition zone acting as a barrier between them. This question, known as the debate between whole mantle convection and layered convection, was one of the most contentious in all of Earth science. The answer, it turns out, is complicated. Seismic tomography, the technique that uses seismic waves to create three-dimensional images of the Earth's interior, has revealed that some subducting slabs penetrate straight through the transition zone and descend all the way to the core mantle boundary. Other slabs appear to stall at the transition zone, spreading out horizontally and accumulating at depths of roughly 660 kilometers before eventually breaking through and continuing their descent. This suggests that mantle convection is neither purely whole mantle nor purely layered, but something in between, a complex, dynamic system in which material can cross the transition zone but sometimes encounters resistance. The deepest part of the mantle, just above the core mantle boundary at a depth of roughly 2,900 kilometers, is one of the most mysterious and fascinating regions of the planet. This region, sometimes called the D-double prime layer, is a zone of extreme contrasts. The temperature difference across this boundary is enormous, with the mantle rock at roughly 2,500 degrees Celsius and the liquid iron of the outer core at roughly 4,000 degrees Celsius. This temperature contrast drives vigorous convection and creates a complex, turbulent environment. It is in this deep region that scientists have discovered the two enormous structures known as large low-shear velocity provinces, or LLSVPs, which we briefly mentioned in Part 1. These structures, one beneath Africa and one beneath the Pacific, are among the largest features in the Earth's interior. They are thousands of kilometers across, hundreds of kilometers tall, and they appear to be compositionally distinct from the surrounding mantle rock, meaning they are made of different material. The origin of the LLSVPs is one of the great unsolved mysteries of Earth science. Some researchers believe they are ancient, primordial structures that have existed since the very earliest days of the planet's formation, possibly remnants of the giant impact that is thought to have created the Moon. According to this hypothesis, when a Mars-sized body called Theia collided with the early Earth roughly 4.5 billion years ago, some of the iron-rich material from Theia's mantle may have sunk to the base of the Earth's mantle and accumulated there, forming the LLSVPs. Other researchers believe the LLSVPs are made of subducted oceanic crust that has accumulated at the base of the mantle over billions of years. Because oceanic crust is denser than normal mantle rock, it would tend to sink to the bottom of the mantle during subduction and pile up above the core mantle boundary. Over billions of years, this accumulated material could form the large, distinct structures that seismic imaging has revealed. Whatever their origin, the LLSVPs appear to play an important role in the dynamics of the mantle and, by extension, in the behavior of the tectonic plates at the surface. Many of the world's hotspot volcanoes, including those in Hawaii, Iceland, and parts of East Africa, appear to be located above the edges of the LLSVPs, suggesting that the plumes of hot material that feed these volcanoes may originate from the boundaries of these deep structures. Some researchers have even suggested that the LLSVPs influence the pattern of mantle convection in a way that affects the locations of mid-ocean ridges, subduction zones, and the overall configuration of the tectonic plates. This is a profound and humbling idea. It suggests that the geography of the Earth's surface, the positions of the continents, the shapes of the ocean basins, the locations of mountain ranges and volcanic hotspots, may ultimately be controlled by structures lurking nearly 3,000 kilometers beneath our feet, structures that have persisted for billions of years and that are utterly beyond our ability to see, touch, or directly observe. Let us now explore one of the most dramatic and geologically active regions on the planet, the Ring of Fire. We mentioned the Ring of Fire in Part 1, but it deserves a much more detailed examination because it is one of the most important and dangerous geological features on Earth. The Ring of Fire is a horseshoe-shaped belt of intense seismic and volcanic activity that encircles the Pacific Ocean. Stretches for roughly 40,000 kilometers, running from the southern tip of the continent south of the Pacific, northward along the western edge of the landmasses bordering the eastern Pacific, across the Aleutian Islands, and southward along the western margin of the Pacific through the Kamchatka Peninsula, Japan, the Philippines, Indonesia, and New Zealand. The Ring of Fire is home to roughly 450 active volcanoes, which is about 75% of all the active volcanoes on Earth. It is the site of approximately 90% of the world's earthquakes, including many of the most powerful earthquakes ever recorded. The reasons for this extraordinary concentration of geological activity are straightforward. The Ring of Fire is defined by the boundaries of the Pacific Plate and several smaller plates, and these boundaries are predominantly subduction zones, where dense oceanic crust is being forced beneath less dense continental or oceanic crust. The geological diversity along the Ring of Fire is remarkable. In the southwestern Pacific, the subduction of the Pacific Plate beneath the Indo-Australian Plate has created the Tonga Trench, one of the deepest points in the world's oceans, and the volcanic islands of Tonga, Samoa, and Fiji. Further north, the subduction of the Pacific Plate beneath the Philippine Sea Plate has created the Mariana Trench, the deepest point on the surface of the Earth, as well as the Mariana Islands. The Challenger Deep, the lowest point in the Mariana Trench, reaches a depth of roughly 10,994 meters below sea level. In Japan, the complex interaction of four tectonic plates, the Pacific Plate, the Philippine Sea Plate, the Eurasian Plate, and the North Plate of the Western Hemisphere's tectonic system, creates one of the most seismically active regions on the planet. Japan experiences hundreds of earthquakes every year, most of which are too small to be felt, but some of which are devastating. The country's entire culture and infrastructure have been shaped by the need to live with the constant threat of earthquakes, tsunamis, and volcanic eruptions. The Indonesian archipelago is another extraordinary product of the Ring of Fire. Indonesia sits at the junction of several tectonic plates, including the Indo-Australian plate, the Eurasian plate, and the Pacific plate, making it one of the most tectonically complex regions on Earth. The country has more active volcanoes than any other nation, roughly 130, and it has experienced some of the most catastrophic volcanic eruptions and earthquakes in recorded history. The eruption of Krakatoa in 1883 is one of the most famous volcanic events in history. The eruption was so powerful that it was heard nearly 5,000 kilometers away, the loudest sound ever recorded in modern history. The eruption destroyed most of the island, generated tsunamis that killed roughly 36,000 people, and injected so much ash and sulfur dioxide into the atmosphere that global temperatures dropped by more than 1 degree Celsius for several years. The sunsets around the world were so vivid and unusual in the months following the eruption that they are believed to have inspired the fiery sky in Edvard Munch's famous painting, The Scream. The eruption of Mount Tambora in 1815, also in Indonesia, was even more powerful. It is considered the largest volcanic eruption in recorded history, with a volcanic explosivity index of 7. The eruption ejected roughly 160 cubic kilometers of material into the atmosphere and killed an estimated 71,000 people, both from the eruption itself and from the famine and disease that followed. As we mentioned in Part 1, the atmospheric effects of the Tambora eruption caused 1816 to be known as the year without a summer, with devastating consequences for agriculture and food supplies across the northern hemisphere. Now let us travel to a very different geological setting, the mid-ocean ridges, and explore the strange and alien world of the deep-sea hydrothermal vents. Mid-ocean ridges are the sites of seafloor spreading, where new oceanic crust is being created by the upwelling of magma from the mantle. Along these ridges, seawater percolates down through cracks and fissures in the newly formed rock, is heated by the hot magma below, and then rises back to the surface, carrying with it a rich cocktail of dissolved minerals. When this superheated water, which can reach temperatures of up to roughly 400 degrees Celsius, encounters the near-freezing water of the deep ocean, the dissolved minerals precipitate out, forming towering chimney-like structures known as hydrothermal vents. These structures, sometimes called black smokers because of the dark, mineral-laden plumes they emit, can grow to heights of several meters. The discovery of hydrothermal vents in 1977 at a site along the Galapagos Rift in the eastern Pacific was one of the most astonishing scientific discoveries of the 20th century. Scientists had expected to find bare, lifeless rock at these depths, far from the reach of sunlight. Instead, they found thriving ecosystems teeming with life, including giant tube worms over a meter long, dense clusters of mussels and clams, and vast colonies of bacteria. These organisms had no need for sunlight. Instead, they derived their energy from the chemical reactions between the mineral-rich vent fluids and the surrounding seawater, a process known as chemosynthesis. The discovery of chemosynthetic life at hydrothermal vents fundamentally changed our understanding of biology. It demonstrated that life does not require sunlight, only a source of chemical energy and liquid water. This insight has had profound implications for the search for life beyond Earth, because it suggests that life could potentially exist in environments that were previously considered too extreme, such as the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus, where hydrothermal vents may also be present. Some scientists have gone even further, suggesting that hydrothermal vents may have been the cradle of life itself. The chemical-rich environment of a hydrothermal vent, with its gradients of temperature, pH, and mineral concentration, could have provided the conditions necessary for the first self-replicating molecules to form, roughly 4 billion years ago. This remains a subject of active debate, but the idea that life on Earth may have originated at a tectonic feature, a place where the planet's internal heat meets the ocean, is a fitting testament to the central role that plate tectonics has played in the story of our world. Let us now turn to a subject that is closely related to plate tectonics but is often overlooked: the role of tectonic forces in shaping the Earth's ocean basins and coastlines. The shapes of the world's ocean basins are entirely the product of tectonic plate movement. The Atlantic Ocean, as we discussed in Part 1, is a relatively young ocean that is still growing as the plates on either side of the mid-Atlantic ridge move apart. The Pacific Ocean, on the other hand, is ancient and shrinking, with its oceanic crust being consumed at subduction zones around its margins. The Indian Ocean was formed by the breakup of Gondwana and the northward movement of the Indian and Australian landmasses. But within these major ocean basins, tectonic forces have created a stunning variety of geological features. Seamounts, for example, are underwater mountains that rise from the ocean floor but do not reach the surface. There are estimated to be more than 100,000 seamounts in the world's oceans, and many of them are extinct volcanoes that formed over hotspots or along mid-ocean ridges. When the tectonic plate carried them away from their source of magma, their volcanic activity ceased, and they began to subside and erode. Some seamounts are flat-topped, having been eroded to sea level by waves before subsiding below the surface as the plate cooled and sank. These flat-topped seamounts are called guyots, named after the Swiss-born geographer Arnold Guyot. The existence of guyots was one of the early pieces of evidence for the theory of plate tectonics, because it demonstrated that the ocean floor is not static but moves and subsides over time. Coral atolls are another geological feature created by the interplay of tectonic plate movement and biological processes. When a volcanic island forms over a hotspot, coral reefs grow around its shores in the warm, shallow water. As the tectonic plate carries the island away from the hotspot, the island subsides and erodes, but the coral reef continues to grow upward, keeping pace with the subsidence. Eventually, the volcanic island disappears entirely beneath the waves, and all that remains is a ring-shaped coral reef surrounding a shallow lagoon, an atoll. Charles Darwin was the first to propose this mechanism for atoll formation in 1842, and his hypothesis has been confirmed by drilling through atolls and finding volcanic rock beneath the coral. The connection between plate tectonics and coastlines extends to the continents as well. Coastlines can be classified as either active or passive margins. An active margin is located at a plate boundary, and it is typically characterized by a narrow continental shelf, steep slopes, and intense geological activity, including earthquakes, volcanic eruptions, and mountain building. The western coast of the large landmass bordering the eastern Pacific is an example of an active margin. A passive margin, by contrast, is located far from a plate boundary and is characterized by a wide continental shelf, gentle slopes, and relative geological quiet. The eastern coast of the same large landmass is an example of a passive margin. Passive margins form when a continent rifts apart and a new ocean basin forms. The edge of the continent, which was once a rift zone, gradually cools and subsides, accumulating thick sequences of sediment that bury the original rift structures and create a broad, flat continental shelf. The distinction between active and passive margins has important practical implications. Passive margins tend to have thick accumulations of sediment that can contain significant reserves of oil and natural gas. Active margins, on the other hand, tend to have more mineral deposits associated with volcanic and hydrothermal activity. The geology of coastlines, and therefore the resources available to the people who live along them, is fundamentally determined by tectonic processes. Let us now venture into the realm of the future and consider what the Earth will look like millions of years from now as the tectonic plates continue their inexorable movement. Predicting the future positions of the continents is an exercise in extrapolation, projecting current plate movements forward in time and accounting for the forces that drive those movements. It is inherently uncertain, because the forces acting on the plates can change over geological time as new subduction zones form old ones close, and the pattern of mantle convection evolves. Nevertheless, geologists have developed several plausible scenarios for the future configuration of the continents, and all of them involve dramatic changes in the world's geography. In the near geological future, say 50 million years from now, several significant changes are expected. The Atlantic Ocean will continue to widen as the plates on either side of the mid-Atlantic ridge move apart. The Pacific Ocean will continue to shrink as its oceanic crust is consumed at subduction zones. The Mediterranean Sea will close as the African plate continues to move northward, colliding with the Eurasian plate. In fact, the collision is already underway, and the Alps and other mountain ranges of southern Europe are the evidence. In 50 million years, the Mediterranean may be completely gone, replaced by a towering mountain range comparable to the Himalayas. East Africa will continue to rift apart along the East African Rift System, and in roughly 10 to 20 million years, the eastern part of the continent will separate completely, forming a new island continent and a new ocean basin. Australia will continue to move northward, and in roughly 50 million years, it may collide with Southeast Asia, creating new mountain ranges and dramatically reshaping the geography of the region. Looking further into the future, roughly 100 to 250 million years from now, the continents are expected to converge again to form a new supercontinent. Several models have been proposed for how this might happen. One model, called Pangaea Ultima or Pangaea Proxima, suggests that the Atlantic Ocean will eventually develop subduction zones along its margins, causing it to begin to close. The continents surrounding the Atlantic will converge, eventually reassembling into a supercontinent that is superficially similar to the original Pangaea, but with a very different internal structure. Another model, called Amasia, suggests that the continents will converge over the North Pole, driven by the northward movement of several major plates. In this scenario, the Arctic Ocean closes, and the continents assemble into a supercontinent centered on the northern polar region. A third model, called Nova Pangaea, suggests that the Pacific Ocean will close entirely as the Pacific Plate is completely consumed at subduction zones. The continents bordering the Pacific will converge, forming a supercontinent in the Eastern Hemisphere. Regardless of which model proves correct, the formation of the next supercontinent will have profound consequences for the planet's climate, ocean circulation, and biosphere. The interior of the supercontinent will be far from the moderating influence of the oceans, leading to extreme temperatures with scorching summers and frigid winters. Ocean circulation patterns will be dramatically altered, affecting the distribution of heat and moisture around the globe. And the consolidation of the continents will reduce the total length of coastline, potentially reducing the diversity of marine habitats and altering the conditions for life. But supercontinents do not last forever. Just as Pangaea broke apart, so too will the next supercontinent eventually rift and fragment, beginning the cycle anew. This is the grand rhythm of the Earth, a slow, majestic cycle of assembly and breakup that has repeated itself at least 3 or 4 times over the last 3 billion years and will continue for as long as the Earth's internal heat is sufficient to drive plate tectonics. Now let us explore a question that has captivated scientists and the public alike. Is there plate tectonics on other worlds? As we discussed in Part 1, Earth is the only planet in our solar system with clear, unambiguous evidence of active plate tectonics. But the search for plate tectonics beyond Earth is an active and exciting area of research, driven in part by the recognition that plate tectonics may be intimately linked to the habitability of a planet. Venus, Earth's near twin in terms of size and composition, is a particularly interesting case. Venus has a thick, hot atmosphere and a surface temperature of roughly 460 degrees Celsius, hot enough to melt lead. Its surface is dominated by volcanic features, including vast lava plains, enormous shield volcanoes, and peculiar structures called coronae, which may be related to the upwelling of hot material from the mantle below. But Venus does not appear to have the system of discrete, moving plates that characterizes Earth. Instead, its surface appears to behave as a single, stagnant lid, with heat escaping from the interior primarily through volcanic activity rather than through the creation and destruction of plates at ridges and subduction zones. Why is Venus so different from Earth? One possibility is the absence of liquid water. As we discussed in Part 1, water plays a crucial role in plate tectonics on Earth. It weakens rocks, lubricates faults, and facilitates the subduction of oceanic crust. Without liquid water, the rocks of Venus's crust and mantle may be too strong and too rigid to allow plate tectonics to operate. Another possibility is that Venus's high surface temperature keeps the crust too hot and too ductile to fracture into rigid plates. Whatever the reason, the absence of plate tectonics on Venus may be one of the factors that has made it so inhospitable to life. Some researchers have suggested that Venus may undergo periodic episodes of catastrophic resurfacing, in which the entire surface of the planet is overturned and replaced by new volcanic rock over a relatively short period of geological time. The evidence for this comes from the relatively uniform age of Venus's surface, which appears to be only about 500 to 700 million years old, based on the density of impact craters. If this hypothesis is correct, Venus may alternate between long periods of geological quiescence and brief, catastrophic episodes of intense volcanic activity, a dramatically different style of tectonics from the continuous, steady-state plate tectonics of Earth. Mars is another world that has been studied in the context of plate tectonics. Mars is much smaller than Earth, and its interior has cooled more rapidly, so it has lost much of the internal heat that drives geological activity. Today, Mars appears to be geologically dead, or nearly so, but there is evidence that Mars may have had some form of tectonic activity early in its history. The dichotomy between the lowland plains of Mars's northern hemisphere and the heavily cratered highlands of the southern hemisphere has been interpreted by some researchers as evidence of an ancient episode of plate tectonics, or at least of some form of large-scale crustal deformation. The enormous Tharsis volcanic province, which includes Olympus Mons, the tallest volcano in the solar system at roughly 22 kilometers high, may also have been influenced by tectonic processes. The Valles Marineris, a system of canyons on Mars that stretches for roughly 4,000 kilometers and reaches depths of up to 7 kilometers, is sometimes compared to rift valleys on Earth and may have formed through extensional tectonics related to the formation of the Tharsis Bulge. But whatever tectonic activity Mars may have experienced, it appears to have ceased billions of years ago, and the planet's surface has been largely static ever since. Beyond our solar system, the question of plate tectonics becomes even more speculative but also more exciting. Thousands of exoplanets have been discovered in recent years, including many rocky Earth-sized planets in the habitable zones of their host stars. Could any of these planets have plate tectonics? The answer is that we do not yet know, because our ability to characterize the geology of exoplanets is extremely limited. But theoretical models suggest that plate tectonics is most likely to occur on planets that are similar to Earth in size, composition, and water content. Planets that are too small may cool too quickly, losing the internal heat needed to drive convection. Planets that are too large may have mantles that are under such extreme pressure that convection is inhibited. And planets without liquid water may lack the lubrication needed for subduction. The search for plate tectonics on exoplanets is intimately connected to the search for life beyond Earth, because plate tectonics may be a prerequisite for long-term planetary habitability. As we discussed in Part 1, plate tectonics plays a crucial role in regulating the Earth's climate through the carbonate-silicate cycle. Without plate tectonics, a planet's climate may not be able to self-regulate, leading to either a runaway greenhouse effect, as appears to have happened on Venus, or a frozen, uninhabitable world. If plate tectonics is indeed necessary for habitability, then the search for plate tectonics on exoplanets is, in a very real sense, a search for the conditions that could support life. Let us now return to Earth and explore some specific geological wonders that are the direct products of tectonic plate activity. The Great Rift Valley of East Africa is one of the most spectacular geological features on the planet, stretching for roughly 6,000 kilometers from the Afar Triangle in the north, through Ethiopia, Kenya, Tanzania, and into Mozambique in the south. The Rift Valley is a place where you can literally watch a continent tearing itself apart. The rift is marked by steep escarpments, active volcanoes, hot springs, and a chain of deep lakes, including Lake Victoria, the largest lake in Africa, and Lake Tanganyika, the second deepest lake in the world. The Afar Triangle at the northern end of the rift is one of the most geologically remarkable places on Earth. It is the only place where a mid-ocean ridge emerges onto land, making it possible to walk on the same type of geological feature that normally lies thousands of meters beneath the surface of the ocean. The Afar Triangle is also a triple junction, a point where three tectonic plates, the African plate, the Somali plate, and the Arabian plate, are all moving apart from each other. The landscape is stark and otherworldly, with vast fields of hardened lava, steaming fissures, and some of the lowest, hottest, and most inhospitable terrain on the planet. The Danakil Depression, located within the Afar Triangle, is one of the lowest points on the Earth's surface, lying roughly 125 meters below sea level, and it holds the record for the highest average annual temperature of any inhabited place on Earth. Iceland is another geological wonder created by plate tectonics. Sitting astride the mid-Atlantic ridge, Iceland is one of the few places on Earth where a divergent plate boundary is visible on land. The island is being pulled apart at a rate of roughly 2 centimeters per year, and the rift running through the center of the country is marked by fissures, volcanic craters, and geothermal features. The Thingvellir Rift Valley, one of Iceland's most iconic landmarks, is a place where you can literally stand in the gap between the Eurasian and the plate to its west, with the walls of the rift rising on either side. Iceland's volcanic activity is driven not only by the divergent plate boundary, but also by a mantle hotspot located beneath the island. This combination of a mid-ocean ridge and a hotspot makes Iceland one of the most volcanically active places on Earth. The eruption of Eyjafjallajökull in 2010, while relatively small by Icelandic standards, disrupted air travel across Europe for weeks, demonstrating the far-reaching consequences of volcanic activity driven by plate tectonics. The eruption of Laki in 1783 was far more devastating. It produced one of the largest lava flows in recorded history, and released enormous quantities of sulfur dioxide and fluorine into the atmosphere, causing widespread crop failures and famine in Iceland, and contributing to unusually cold weather across Europe. The island nation of Japan offers yet another window into the power of tectonic forces. Japan sits at the intersection of 4 tectonic plates, and its geological history is a story of collisions, subduction, and volcanic activity. The Japanese archipelago is essentially a series of volcanic island arcs built by the magma generated at multiple subduction zones. Mount Fuji, perhaps the most iconic volcano in the world, is a product of the subduction of the Philippine Sea plate beneath the Eurasian plate. It last erupted in 1707, and while it is currently dormant, it is not extinct, and scientists monitor it closely for signs of renewed activity. Japan's experience with earthquakes and tsunamis has shaped its society in profound ways. The country has invested heavily in earthquake-resistant construction, early warning systems, and disaster preparedness. Buildings in Japan are designed to flex and sway during earthquakes rather than resist the motion rigidly, a design philosophy that has saved countless lives. Japan's national building code is one of the most stringent in the world, and it is continuously updated based on lessons learned from past disasters. The 2011 Tohoku earthquake and tsunami, which we discussed in Part 1, was a painful reminder that even the most prepared society is not immune to the awesome power of tectonic forces. The earthquake, with a magnitude of 9, was the most powerful ever recorded in Japan's history, and the resulting tsunami overwhelmed coastal defenses that had been designed to withstand smaller waves. The disaster killed over 18,000 people, displaced hundreds of thousands more, and triggered a nuclear crisis at the Fukushima Daiichi power plant that is still being dealt with today. The Tohoku disaster has led to a fundamental reassessment of earthquake and tsunami risk in Japan and has driven further improvements in disaster preparedness and infrastructure design. Now let us explore the geological history of the Mediterranean region, one of the most tectonically complex areas on the planet. The Mediterranean Sea is a remnant of the ancient Tethys Ocean, which once separated the supercontinents of Laurasia and Gondwana. As the African plate has moved northward over the last 100 million years, it has gradually closed the Tethys, squeezing the Mediterranean into an ever smaller basin. The collision between the African and Eurasian plates has created the Alps, the Apennines, the Carpathians, the Atlas Mountains, and numerous other mountain ranges around the Mediterranean rim. The Mediterranean region is seismically active, and destructive earthquakes are a recurring feature of its history. The 1908 Messina earthquake in Italy, with a magnitude of roughly 7.1, destroyed the cities of Messina and Reggio Calabria and killed an estimated 75,000 to 200,000 people, making it one of the deadliest earthquakes in European history. The region is also volcanically active, with Mount Etna in Sicily, Mount Vesuvius near Naples, and the volcanic island of Stromboli among the most well-known volcanoes. One of the most extraordinary events in the geological history of the Mediterranean is the Messinian salinity crisis, which occurred roughly 5.9 to 5.3 million years ago. During this period, tectonic movements caused the strait connecting the Mediterranean to the Atlantic Ocean to close. Cut off from its main source of water, the Mediterranean began to evaporate. Over a period of roughly 600,000 years, the Mediterranean may have dried up almost completely, leaving behind vast deposits of salt and gypsum on the former seabed. The basin, thousands of meters deep in places, would have been an extraordinarily inhospitable environment, with temperatures at the bottom reaching extreme highs due to the adiabatic effect of the depressed elevation. The Messinian salinity crisis ended roughly 5.3 million years ago when the barrier to the Atlantic was breached, possibly catastrophically. Some researchers have suggested that the refilling of the Mediterranean, known as the Zanclean Flood, may have been one of the most dramatic geological events in recent Earth history, with water pouring through the breach at a rate that dwarfs any flood in human experience. The refilling may have taken only a few thousand years, or possibly even less, depending on the size of the breach. This event, driven entirely by tectonic forces that opened and closed the gateway between the Mediterranean and the Atlantic, had profound consequences for the climate, ecology, and geography of the entire region. Let us now consider the role of plate tectonics in the formation of some of the world's most important geological features and resources, starting with the mineral wealth of South Africa. The Witwatersrand Basin in South Africa has produced roughly 40% of all the gold ever mined on Earth. This extraordinary concentration of gold is the result of a complex geological history involving tectonic processes. The gold was originally deposited roughly 2.7 to 3 billion years ago in sedimentary rocks that formed in a basin created by tectonic subsidence. The exact origin of the gold is debated, but it may have been derived from the erosion of ancient gold-bearing volcanic rocks and concentrated by the action of rivers and streams that flowed into the basin. Subsequent tectonic events, including mountain-building episodes and the intrusion of igneous rocks, helped to preserve and, in some cases, further concentrate the gold deposits. The diamond-bearing kimberlite pipes of southern Africa are another example of tectonic forces creating mineral wealth. Kimberlites are volcanic rocks that originate deep within the mantle, at depths of 150 kilometers or more, and are brought to the surface by explosive volcanic eruptions. The diamonds they carry were formed under the extreme pressures and temperatures found at those depths, and they owe their existence to the recycling of carbon through the mantle by subduction and other tectonic processes. The copper deposits of Chile, which are among the largest in the world, are directly related to the subduction of the Nazca Plate beneath the South Continental Plate to its east. The magma generated by the subduction process carries copper and other metals from the deep earth to the surface, where they are concentrated by hydrothermal fluids and deposited in the rocks above the subduction zone. These porphyry copper deposits are the primary source of the world's copper supply, and they are a direct gift of plate tectonics. Let us now return to the subject of earthquakes and explore some of the ways in which scientists are working to better understand and predict these devastating events. Despite decades of research, the reliable prediction of earthquakes remains one of the greatest unsolved problems in science. While we can identify regions that are at high risk for earthquakes based on their proximity to plate boundaries and their geological history, we cannot predict the exact time, location, and magnitude of an individual earthquake with any useful degree of precision. The reason for this is the inherent complexity of the fault systems that produce earthquakes. The behavior of a fault depends on a vast number of variables, including the stress state of the rock, the presence and distribution of fluids, the geometry of the fault, the friction along the fault surface, and the interactions between neighboring faults. These variables are extremely difficult to measure directly, especially at the depths where earthquakes originate. Nevertheless, significant progress has been made in earthquake science. Paleoseismology, the study of ancient earthquakes preserved in the geological record, has allowed scientists to determine the recurrence intervals of large earthquakes on specific faults. By trenching across faults and examining the layers of sediment that have been displaced by past earthquakes, paleoseismologists can identify individual earthquake events and determine when they occurred, sometimes with surprising precision. This information is invaluable for assessing the long-term seismic hazard of a region. Geodetic measurements using GPS and satellite-based techniques have allowed scientists to measure the buildup of strain along faults in real time. When a fault is locked, the strain accumulates as elastic deformation of the surrounding rock, much like a rubber band being stretched. By measuring this deformation, scientists can estimate the amount of strain that has accumulated and the approximate magnitude of the earthquake that would be needed to release it. However, knowing how much strain has accumulated does not tell you when the fault will rupture. The strain may continue to build for decades or centuries before being released. One of the most promising developments in earthquake science is the deployment of earthquake early warning systems. These systems exploit the fact that seismic waves travel at finite speeds, roughly 6 to 8 kilometers per second for P waves and 3 to 5 kilometers per second for S waves. By detecting the initial P waves from an earthquake at seismograph stations near the epicenter, the system can calculate the location and magnitude of the earthquake and send a warning to more distant locations before the more damaging S waves and surface waves arrive. The warning time is typically only seconds to tens of seconds, but even a few seconds of warning can be enough to stop trains, shut down industrial processes, open fire station doors, and allow people to take cover. Japan has one of the most advanced earthquake early warning systems in the world, and it provided crucial seconds of warning before the 2011 Tohoku earthquake. Similar systems have been developed or are under development in several other seismically active countries, including Mexico, Taiwan, and nations along the Pacific Rim. Let us now delve into the concept of plate tectonics and its relationship to the origin of life on Earth. We touched on this subject briefly when we discussed hydrothermal vents, but the connection between plate tectonics and the origin of life goes much deeper. Many scientists believe that the conditions necessary for the origin of life, liquid water, a source of energy, the right chemical building blocks, and a mechanism for concentrating and organizing those building blocks, may all have been provided, directly or indirectly, by tectonic processes. The early Earth, during the Hadean and early Archean eons, was a dramatically different place from the world we know today. The atmosphere was rich in carbon dioxide, methane, and water vapor, with little or no free oxygen. The oceans were hot, perhaps as warm as 70 to 80 degrees Celsius, and they were acidic, rich in dissolved iron and other metals. Volcanic activity was far more intense than today, driven by the greater internal heat of the young planet. And it was in this environment that life first appeared, roughly 3.8 to 4 billion years ago. The exact mechanism by which life arose is still unknown, and it is one of the deepest and most fascinating questions in all of science. But many of the leading hypotheses involve geological settings that are directly related to tectonic activity. Hydrothermal vents, as we discussed, provide a source of chemical energy and a rich supply of dissolved minerals. Volcanic hot springs on land provide similar conditions. And the cycling of water through the crust, driven by the heat of the mantle, creates chemical gradients that could have been exploited by the earliest metabolic systems. Some researchers have proposed that the subduction process itself may have played a role in the origin of life, by recycling material between the surface and the interior and creating the chemical diversity that is necessary for complex chemistry. Others have suggested that the serpentinization of ultramafic rocks, a process in which mantle rocks react with water to produce hydrogen gas and other chemicals, may have provided the energy and raw materials for the first living organisms. Serpentinization is most common at slow-spreading mid-ocean ridges and in subduction zones, both of which are tectonic features. If plate tectonics was indeed a prerequisite for the origin of life on Earth, it has profound implications for the search for life elsewhere in the universe. It suggests that life may be most likely to arise on planets with active plate tectonics, which, as we discussed, may require a specific combination of size, composition, internal heat, and surface water. This narrows the search for habitable worlds, but also provides a set of criteria that astronomers can use to prioritize targets for future study. Let us now explore the fascinating phenomenon of induced seismicity, earthquakes that are caused not by natural tectonic forces, but by human activity. It may seem surprising that human beings can cause earthquakes, but it is an established scientific fact. Induced seismicity can be triggered by a variety of human activities, including the injection of fluids into the ground, the extraction of fluids or gas from underground reservoirs, the filling of large reservoirs behind dams, and underground mining. The injection of wastewater into deep disposal wells has been linked to significant increases in earthquake activity in several regions. In one notable case, a region that had historically experienced very few earthquakes saw a dramatic increase in seismic activity, with hundreds of earthquakes per year, after large volumes of wastewater from oil and gas operations were injected into deep wells. Most of these induced earthquakes were small, but some reached magnitudes of 5 or more, large enough to cause damage to buildings and infrastructure. The mechanism is straightforward. When fluid is injected into the ground, it increases the pressure in the pore spaces within the rock. This increased pore pressure reduces the friction on pre-existing faults, making it easier for the faults to slip. In effect, the injected fluid lubricates the faults, triggering earthquakes that might not have occurred for decades or centuries under natural conditions. The filling of large reservoirs behind dams can also trigger earthquakes, a phenomenon known as reservoir-induced seismicity. The weight of the water in the reservoir increases the stress on the underlying rock, and the water can infiltrate faults and increase pore pressure. The most famous example is the Koyna Dam in India, where the filling of the reservoir in the 1960s triggered a series of earthquakes, including a magnitude 6.3 event in 1967 that killed roughly 180 people. Mining can also trigger earthquakes, particularly deep underground mining in seismically active regions. The removal of large volumes of rock changes the stress state of the surrounding rock, and the resulting adjustments can trigger seismic events. In South Africa, deep gold mines in the Witwatersrand Basin regularly experience mining-induced earthquakes, some of which are large enough to cause fatalities and significant damage to mine infrastructure. The phenomenon of induced seismicity raises important questions about the interaction between human activity and natural tectonic forces. While induced earthquakes are generally smaller than the largest natural earthquakes, they can still be damaging, particularly in regions where the infrastructure was not designed to withstand seismic shaking. The management of induced seismicity is an active area of research and policy, and it requires a careful balance between the economic benefits of resource extraction and the need to protect public safety. Now let us consider one of the most profound and far-reaching consequences of plate tectonics, its role in shaping the evolution of the Earth's atmosphere and oceans over geological time. The Earth's atmosphere has changed dramatically over the course of the planet's history, and plate tectonics has been a major driver of those changes. The early atmosphere, as we mentioned, was rich in carbon dioxide and methane, with little or no free oxygen. This was actually essential for the early Earth because the Sun was roughly 30% dimmer 4 billion years ago than it is today, and without the strong greenhouse effect provided by these gases, the Earth would have been frozen solid, the so-called faint young sun paradox. Plate tectonics help to maintain the greenhouse effect by continuously releasing carbon dioxide through volcanic eruptions. As the Sun gradually brightened over billions of years, the carbonate silicate cycle, regulated by plate tectonics, gradually drew down carbon dioxide levels, preventing the Earth from overheating. This self-regulating mechanism has kept the Earth's surface temperature within the range necessary for liquid water, and therefore for life for most of the planet's history. The rise of atmospheric oxygen, one of the most important events in the history of life, was also influenced by tectonic processes. Free oxygen began to accumulate in the atmosphere roughly 2.4 billion years ago, during an event known as the Great Oxidation Event. This oxygen was produced by cyanobacteria, photosynthetic organisms that split water molecules and released oxygen as a byproduct. But for oxygen to accumulate in the atmosphere, the rate of oxygen production had to exceed the rate at which oxygen was consumed by chemical reactions with iron and other reduced substances in the rocks and oceans. Tectonic processes played a role in tipping this balance. The burial of organic carbon in sedimentary basins, which removes a sink for oxygen, is enhanced by tectonic subsidence and the creation of sedimentary environments. The oxidation of reduced gases released by volcanic activity also consumes oxygen, and changes in the rate and composition of volcanic emissions, driven by changes in tectonic activity, may have influenced the timing and pace of the Great Oxidation Event. The composition of the oceans has also been profoundly influenced by plate tectonics. The salinity of the oceans, for example, is maintained by a balance between the input of dissolved minerals from rivers and hydrothermal vents and the removal of those minerals by chemical and biological processes. Both the input and removal of minerals are influenced by tectonic activity. Rivers carry dissolved minerals from the continents to the oceans, and the rate of this input depends on the rate of weathering and erosion, which in turn depends on the uplift of mountain ranges and the exposure of fresh rock by tectonic processes. Hydrothermal vents at mid-ocean ridges are a significant source of some elements, including iron, manganese, and lithium, and a sink for others, including magnesium and sulfate. The cycling of sulfur through the Earth system is another example of how plate tectonics influences ocean chemistry. Sulfate in the ocean is derived from the weathering of sulfur-bearing minerals on land and from volcanic emissions. Sulfate is removed from the ocean by the formation of evaporite minerals in shallow basins, and by the reduction of sulfate to sulfide by microorganisms in anoxic environments. The balance between these processes, which determines the sulfate concentration of the ocean, is influenced by the arrangement of the continents, the distribution of shallow seas, and the rate of volcanic activity, all of which are controlled by plate tectonics. Let us now explore the fascinating subject of paleogeography, the study of the ancient geography of the Earth. Paleogeographic reconstructions, maps of the Earth at various points in the geological past, are one of the most powerful tools for understanding the history of plate tectonics and its effects on climate, ocean circulation, and life. These maps are constructed using a wide range of geological data, including the paleomagnetic record, the distribution of fossils, the ages and compositions of rocks, and the geometry of geological structures. One of the most striking aspects of paleogeographic reconstructions is the sheer magnitude of the changes that have occurred. 500 million years ago, during the Cambrian period, the continents were arranged in a configuration that would be completely unrecognizable to a modern observer. Most of the major landmasses were clustered in the southern hemisphere, and a vast ocean, the Apetus Ocean, covered much of what is now the northern hemisphere. 300 million years ago, during the late Carboniferous period, the continents had converged to form the supercontinent Pangaea, with a single global ocean, Panthalassa, covering the rest of the planet. And 200 million years ago, Pangaea began to break apart, setting in motion the series of rifting events that would eventually produce the modern geography of the Earth. These paleogeographic changes have had profound effects on the evolution of life. During the Cambrian period, when the continents were scattered and the shallow seas were extensive, there was an extraordinary explosion of marine biodiversity, the Cambrian explosion. The assembly of Pangaea during the late Paleozoic era reduced the total length of coastline and the extent of shallow marine environments, contributing to a decline in marine biodiversity that culminated in the Permian-Triassic mass extinction. The breakup of Pangaea, beginning in the Mesozoic era, created new ocean basins, new coastlines, and new shallow seas, providing new habitats and driving a new burst of diversification that ultimately led to the rich biodiversity of the modern world. Let us also consider the role of plate tectonics in the formation of the Earth's magnetic field and the protection it provides against harmful radiation from space. The Earth's magnetic field is generated by the convection of liquid iron in the outer core, a process known as the geodynamo. While the magnetic field is not directly generated by plate tectonics, the two are linked through the thermal evolution of the planet. The heat lost from the core drives the convection that generates the magnetic field, and this heat is ultimately transferred to the surface and radiated into space through the mantle and the crust. Plate tectonics, by facilitating the transport of heat from the interior to the surface, plays an indirect but important role in maintaining the conditions necessary for the geodynamo to operate. The magnetic field protects the Earth's atmosphere from being stripped away by the solar wind, a stream of charged particles constantly emanating from the sun. Without the magnetic field, the solar wind would gradually erode the atmosphere, and the Earth would lose its air and water, becoming a barren, lifeless world like Mars. Mars, which lacks a global magnetic field, has lost most of its original atmosphere over the last few billion years, and its surface is now cold, dry, and exposed to harmful radiation. The link between plate tectonics, the geodynamo, and the preservation of the atmosphere is another way in which plate tectonics may be essential for planetary habitability. A planet with plate tectonics is more likely to have a strong magnetic field, a thick atmosphere, liquid water, and a regulated climate, all of which are prerequisites for life as we know it. As we approach the conclusion of this documentary, let us step back and consider the big picture. Plate tectonics is not just a geological process. It is the master sculptor of the planet, the engine that drives nearly every major geological and environmental process on Earth. It builds mountains and tears them down. It opens oceans and closes them. It creates the conditions for life and occasionally devastates life through volcanic eruptions and earthquakes. It regulates the climate, shapes the composition of the atmosphere and oceans, and influences the evolution of every living thing on the planet. The theory of plate tectonics, developed over the course of the 20th century and continuously refined by new discoveries and new technologies, is one of the greatest intellectual achievements of humanity. It provides a unifying framework for understanding the Earth, connecting phenomena as diverse as earthquakes, volcanic eruptions, mountain building, ocean formation, mineral deposits, climate change, and the evolution of life into a single, coherent narrative. It has transformed geology from a descriptive science into a predictive one, allowing us to understand not only what has happened in the past, but also what is likely to happen in the future. And yet, for all our knowledge, there is still so much that we do not understand. The exact mechanisms by which plates initiate subduction, the role of the deep mantle in controlling plate motion, the conditions under which plate tectonics can arise on other planets, the detailed history of the earliest tectonic activity on Earth, these are all questions that remain open and that are the subject of intense ongoing research. What we do know is that the Earth is a dynamic, living planet, one that is constantly changing, constantly evolving, and constantly reshaping itself through the relentless movement of its tectonic plates. The ground beneath your feet is not solid and permanent. It is moving slowly but surely, carrying you on a journey that began billions of years ago and that will continue for billions of years to come. Every mountain you see was once a flat plain. Every ocean was once a rift in a continent. Every continent was once a fragment of a larger landmass, and every feature of the landscape, from the smallest hill to the grandest mountain range, is a product of the same fundamental process, the movement of the tectonic plates. The next time you feel the ground shake during an earthquake, or see a volcano erupting on the news, or gaze at a mountain range rising against the sky, remember that you are witnessing the forces of plate tectonics at work. These are the same forces that have been shaping the Earth for 4.5 billion years, the same forces that created the world as you know it, and the same forces that will continue to reshape it long after you are gone. We are passengers on a planet in motion, riding on slabs of rock that are carried by currents of heat from deep within the Earth. We did not choose this journey, and we cannot control it, but we can try to understand it. And in understanding it, we gain not only knowledge, but also a profound sense of awe and humility before the vast, patient, and inexorable forces that govern our world. This has been the story of tectonic plates, the unstoppable force beneath our feet. Thank you for joining us on this journey through one of the most extraordinary chapters of the Earth's story. The plates will keep moving, the continents will keep drifting, the mountains will keep rising. And the Earth will keep telling its story, written in stone, for anyone who takes the time to read it.